Hello, everyone. I'm Manish. I work in the research group at Merit, and today I'll be talking about some of the work we're doing in analyzing darknet traffic. In particular, I'll be focusing on our analysis of the 1/8 address space, which was recently allocated, and try to generalize from that afterward as to what can we do, what can we learn from this address space. So moving on, so we're now down to the last 16/8s in the IPv4 that are still not allocated. There's a growing concern that these blocks are less desirable or are likely to be less usable in some way. Someone on the NANOG, some wise man on the NANOG post once said, the water at the bottom of the barrel is probably not going to be very pure, and that's sort of what this talk is all about, looking at how do we figure out what's going on in the leftover space. So what recently in January, INA allocated 1/8 to APNEC, and 1/8 has been used in various examples and applications and test cases. So there was some concern that this might not be a very desirable address block. That's what today's talk is all about. We tried to take a look at what is a normal amount of pollution traffic in an unallocated block. Was the 1/8 different in any way in terms of the amount of traffic, the protocols, the ports? If it is different, why is it different? And in particular, and this is really the most important point, what can we do about it, if anything at all? So the first evidence that something was not quite right with the 1/8, well, we knew anecdotally that something was not right, but the first real experimental evidence of this was from the RIPE allocation of their from their debogonizing experiment in January. And what they quickly noticed was when they announced their debogon prefixes, they maxed out their 10 megabit per second link. So right away, there was the first evidence that something was not right. Here's a summary chart from their nice Albatross tool, which talks about advertisements from the 1/8 subblock. And what you can see is the blue line shows when the 1/8 was actually allocated. And prior to that, the x-axis is the entire month of January. And you can see there are several allocations from the 1/8. Several BGP announcements which are dealing with address spaces from the 1/8 just popping up in the BGP tables. So we set out to try to do an experiment. We worked with APNIC to try to figure out what this traffic was and where it was coming from. We announced 1/8 for about a 10-day time period, 8 to 10 days. We collected about 8 terabytes of packet captures, full packet captures. And here's the traffic that we observed. So what you're looking at, the graphs on the y-axis is millions of packets, sorry, megabits per second is the y-axis, and the x-axis is the week-long duration. And roughly what you're looking at is 160 to 170 megabits per second of sustained traffic for the entire /8. Here's the packet rate. There are some peaks that are exceptionally high as 200 kilo packets per second. We believe those to be scanning events of somebody just trying to scan, 1/8. But even in terms of the millions of packets per second, average, we're looking at about 150,000 packets per second on average. So how normal is this? Is this what darkening traffic is supposed to be? So what we did was we looked at traffic that we already had from another /8, which is the 35/8, which is largely unallocated except for a small, portions, a small /17 block in it. So we compared the total volume. On the left, you'll see the total volume for the 1/8, which was about 150 megabits per second. And on the right-hand side, the 35/8 was measured at a 15 to 25 megabits per second. So right away, there's a huge difference in the traffic volume that we're seeing. Protocol distribution was another thing that is very obviously different between these two blocks. For the 1/8, UDP dominates very, very heavily, whereas for the 35/8, it's TCP that's the dominating traffic volume. When we're comparing the types of pollution that we're seeing on these two darknets, the 1/8, for example, we measured about 17 to 20% of scanning traffic, 2% of backscatter, and other or misconfigured traffic was clocked at about 80% of it. We were like, we don't know what this is. We need to take another look. For the 35/8, there's a huge difference. So the scanning traffic is similar in nature. You would expect that scanning traffic would be similar because people are likely scanning these dark spaces equally. Same with backscatter. You wouldn't expect some backscatter subnets to be worse than others. And that sort of plays out a little bit here. But the misconfiguration percentages are what really stand out. So what's going on? So we looked at the traffic destinations in the 1/8 and sliced it up into /16 net blocks. And on the y-axis, we're plotting the volume of traffic for each /16. And you can see clearly there are very sharp, well-defined spikes, which are highlighting certain areas of this 1/8 which are seeing large amounts of traffic. So we did a deep dive into this data and divided it by measuring volume for each /24. And this was the top 10 list of /24 blocks within the 1/8 that were seeing different amount of traffic volumes. As you can see, the 1110/24 sees almost 45% of the traffic. Clearly, a lot of people are doing quick tests to see where if their protocols, routers, everything is working correctly. We see almost 17% of traffic going to 1400, and and the rest is distributed fairly well across many different things. Yes?
Just a slightly, I wonder if you did a correlation versus sample configs in router vendor documentation and websites.
So in the next few slides, I will talk about a little bit more detail of what is actually making up this traffic, and you will see for yourself where this traffic is coming from and whether it's actually coming from those router configs or not. So the first largest volume we looked at was a top contributor here, which is the 111/24, and within that /24, we found that one particular address was accounting for almost 50% of all the bytes received. And that was the 1.1.1.1 port number 15206. This is UDP traffic. So comparing this to once again to our benchmark /8, which is the 35, you see that this is a huge anomaly. So what are these? So we said, we have the full PCAPs. Let's take a look to see what these packets really are. They appeared to be RTP packets. 75% of all the bytes had the first 16 bits as a 8000. The majority of the packets were all 214 bytes, and about 97% of them were on even ports, hinting at perhaps RTP data packet streams. Where were they coming from? Well, over one day of data, there were only about 1,000 distinct /24s that were sourcing this traffic, and the source ports there were only about 1,600 or so unique source ports that were sending this large volume of traffic. Well, as it turns out, it was audio traffic. We took one stream from a source and used Wireshark to sort of extract or reconstruct the audio stream. And let's see if we can actually play this thing.
Service. Please check the number and try again.
So yes, it was humorous, as surprising as it was. We tried to figure out why this was happening, why we're getting busy messages to darknets. And what turns out is this seems to be the side effect of a SIP invite attack. Whether you want to call it an attack or a misconfiguration, but essentially what's happening is they're either misconfigured SIP servers or this is a legitimate attack where this is essentially backscatter from SIP coming to the darknet. And it's configured to come to 1.1.1. So another large volume of traffic we found was going to the 1.400 subnet. We took another closer look at it, and 17% of these packets were UDP packets. There were different destination port numbers, but when you're using Wireshark, we found we could interpret these as DNS traffic types, and we found that there were different types of DNS packets, quad A's, MX's. We tried to track down sources where they were coming from. We did some profiling of those sources. They all appeared to be coming from an ADSL modem. What exactly the real cause is, we don't know, whether it's misconfigured firmware or misconfigured default configuration, which results in these traffic types being bounced to the darknet. But the queries were essentially all the kinds of queries that would come from an embedded web page. So it's not users typing in a DNS entry and then being directed here. It's essentially results being displayed on a page, and then the embedded DNS queries are what are showing up here. Another fairly significant volume of traffic was to the 1230/24. This was about 2% of all the traffic. And as it turns out, this was iPerf traffic. So people are testing by sending UDP streams to 1/8. The top contributor, so of course the traffic volume is somewhat limited. It's coming from about 100 different unique sources across the internet. The top contributor alone was sending about 70 million packets per second. Here's another interesting contributor of the traffic. So this is essentially, what we noticed was there's some other very popular destinations where we see significant hotspot activity. This was the 11168.0, the 10168.0. They look vaguely familiar, so we're like, what's wrong with us? And of course, what it turns out is these are actually 192.168x.1 addresses with the host byte order turned around. So what's happening is there's somebody who hasn't done a correct host byte order translation in their program, and it's resulting in traffic not going to the right place. So given all these strange activities that we were able to spot, we were working with APNIC in this experiment, of course, and their purpose in this was to figure out what can they actually do with this 1/8. So APNIC has suggested the following recommendations in terms of addresses or net blocks that should be quarantined effectively. The 10024, the 111/24, and there were some other hotspots that needed further digging, which they say we will reserve them at least temporarily till we try to clean up some of this activity. But the question was, would any of this actually make any difference, right? So you go through this exercise of quarantining the address space, or cleaning it up, contacting the sources of this malicious this unknown traffic. So these are two graphs. The one on the left, the before, is showing you the CDF distribution of destination traffic within the 1/80. So what you're seeing is the percentage contribution to the total traffic by a given percentage of the sources. So the red and the green curves are showing you the traffic, the CDF graph for the 1/8. And what you're seeing is very few addresses are accounting for the vast majority of the traffic. That's why the curve is starting right at the top. The purple and the blue line are for the 35 net, and you see a fairly even distribution of traffic volumes to destinations within the 35 net. If we were to subtract the top 10 polluted destinations in the 1/8, this is what the after curve would look like, which is relatively less hotspotting, and therefore you're probably much more usable in terms of address space. There's an interesting kink in the 35/8 curve actually, which is actually a side effect of configure, the way configure targets address space. But that's a whole another talk. So taking the broader view, so we did this study on the 1/8. What did we learn, and where do we go from here? Right? So this was not the only study. We've also found evidence of similar types of pollution in the 50, the 107, the 14, and the 223/8s. All of these have been recently allocated. And what we've learned is they're all dark spaces, but each dark space is different. And each dark space is different because of the strange because hotspots exist in strange and unusual places, and they're very hard to predict where you might find one. So the types of pollution we've come across, in addition to scanning and backscatter, which are everywhere, system misconfiguration, like syslog and DNS. For example, there was one software vendor out in Germany who had an error in their email systems, which was sending syslog to the 50/8. So we were analyzing 50/8 packets and found tons and tons of syslog messages coming from their systems. We contacted them, and they said, "Oh yeah, this is an error. We'll fix it. Don't worry about it." Other places which result in darknet traffic, programming errors. There's some bit-torn traffic that's showing up in these different darknets. There's definitely the bug, the byte order conversion bug that I talked about. There can be hard-coded defaults. such as in the case of the SIP traffic that I pointed out, or the DSL modem traffic, the DNS traffic. And in some cases, experiments gone wild. I mean, somebody started an iPerf test and thought they'd killed it, and they never had, and it's still running out there. It's hard to predict where this is going to come from. So what we needed to do, what we were trying to get towards was a consistent method for identifying these hotspots, and then perhaps developing a policy of how do we quarantine these, how do we try to clean them up, is it even worth our while to do this? So here's the general framework that we've used in most of our experiments. We work with the IRRs to identify upcoming allocations. We obtain clear LOAs so that AT&T won't just drop our announcements, which is, so they're our upstream, so they need a clear letter that says, yes, Merit is going to do these weird announcements. We then advertise the data, we collect it, archive it, and then eventually provide it to the broader research community, other than just us, who want to do their own analysis of this darknet traffic. And then finally, to see if we can develop recommendations regarding cleanup or quarantine. So the conclusions from our studies are unchecked internet pollution does have the potential to render portions of address space unusable. In some cases, cleanup is possible. I mean, if you wanted to spend the time, you could contact every single one of those sources and tell them that they're either, misconfigured or they're generating malicious traffic. If you could find somebody responsible in that net block, definitely a time-consuming endeavor. But maybe eventually it is worth somebody's while as address space starts to run out. And then there's a bigger problem that the internet pollution is just one aspect of the usability of an address block. Reclaimed address space may be on spam blocks, maybe on botnet lists, maybe otherwise blocked in other ways. The current approach is when you do end up with such a block, you just take it back to your RIR and say, can I get a different allocation, please, because this is not working for me. But that might not work for very much longer. There are only 16/8s left and rapidly declining. In fact, between the time that we submitted a draft for this talk and today, I had to update it. It went, the number of available /8s dropped from 22 to 16 in about 3 months. There's also an interesting question about who is really responsible for the quality of the address space, right? The RIRs clearly say, we just give you space. We don't really care whether it's usable or not. But then again, in a way, who else do you talk to? We have collected data for about 8/8s right now. We have 2 more in the works over the next few weeks. It's roughly 10 terabytes of data that we've collected. We will be making this available to the research community as well as the operations community should you care to look at the PCAPs yourself. This will be all made available through the Predict data repository that we're a part of. So, here's some additional materials that you can read up some more about. We have a tech report out on some of our analysis. Some of the graphs are available on that software/darknet website as well. And then APNIC has their own analysis write-ups of these studies as well. And of course, here's the obligatory XKCD reference. So this one really struck us because it showed up around about the same time when we were doing our studies. Was we're looking at this darknet traffic and we're seeing voice calls from private space. Thank you. Questions?
Yeah, we have a little time. We can take a few questions.
Yeah, thanks for the presentation, Danny McPherson. I had 2 questions actually. One is, I certainly agree with the need for discussion on an RIR allocating address space and the usability of that address space and what obligations they may have regarding that. I'm wondering if setting a precedent might be a good or bad thing, or if RIR folk have opinions on that and what amount of work should go into that. That's sort of aside because it's more of a policy thing. I think it would be interesting to look at the acceptance of those address space. You said you had a letter of authorization or whatever it was that said you could announce that, which really doesn't mean anything in the routing system, I guess. But looking at who accepts those routing announcements and maybe filtering them based on bogon and the sort of the control plane in the routing system, but also if there are sort of AS topology preferences based on people that might be doing data path filtering of those bogons, and because that might help with the usability as well, not from an activity perspective, but from a routability and usability perspective for reachability. So does that make sense? Did you guys do any? I haven't read the tech report, but.
Right. No, I think what you're saying makes sense. We have considered broadening the data collection itself to multiple locations. So we want to do data collections not just from Merit, but from the Asia region and the European region, and possibly others as well. And that would give us a much better view of how this darknet traffic varies depending on different parts or the acceptability of the prefix announcement by different portions of the internet. You're right in the sense that before the announcement, this space was not deboganized, and we don't know the actual effectiveness of any deboganizing that does happen. So yeah, but we do see very similar patterns in each /8 in terms of traffic volumes. So we tend to think that whatever that is, it's fairly standard in terms of either people are following good practices and have, they're taking them off the block list quickly, or they're not.
Right.
So
I mean, it might be interesting to collaborate, I guess, to correlate the when this is deboganized with what uptick in activity you see, and and then the routability part. But I think you understand what I was aiming at there.
Absolutely.
So it would be interesting. Thank you.
Thanks. Good suggestion.
Yes, in your presentation, you showed the difference between TCP and UDP, and I noticed that the 35 networks seem to have substantially more TCP. UDP to a darknet to me seems mostly to be misconfiguration, in that it's just going to be flowing out there, and there's no connection-oriented nature to it. The TCP traffic you're seeing in the 35, doing any analysis on that? Is it basically port scanning, people looking for open mail relays? What's the nature of the TCP traffic that you're seeing, and how did that differ between the 1 and the 35 networks? So
the TCP traffic is actually very similar in nature, because it's largely it largely consists of scanning activity as well as SYN resets, SYN-ACKs or SYN resets from denial of service attacks. So that traffic was actually very similar between the darknets.
Thank you.
Yep. John Curran, Aaron. I'd like to thank APNIC, Merit, and UMISH for this work. It's excellent. It could be seen as a study of darknet traffic, but it could also be seen as a study into the non-deployment of reverse path forwarding. There's a lot of traffic that's getting out there that people are sending that for some reason ISPs don't mind forwarding. And I guess I'm wondering if we want to handle this problem on a more general basis for all of the networks that may be near the bottom of the barrel. I'm wondering, sort of more from the community than your presentation in particular, why wouldn't we do some more with RPF to get that deployed, which would cut down on this traffic?
I think it's an excellent point. I mean, we're just at the stage where we're trying to figure out what this traffic is and whether it's worth concerted effort. There's clearly a need for either developing a community-based list of quarantine blocks or even recommended RPF policies that everybody should deploy. But you can only make those recommendations. You can't make people do it.
Okay, thanks.